Hello students, welcome back. In this part of lecture, we are going to discuss about the calculation of gravitational field and gravitational potential at various points due to various shapes. Shapes like gravitational field and gravitational potential due to ring, gravitational field and gravitational potential due to disk, gravitational field and gravitational potential due to hollow sphere, as well as we are also going to discuss about gravitational field and gravitational potential due to solid sphere. Hello students, let's continue the calculation of gravitational field and gravitational potential at various points. We have already studied at due to point mass. Now we are continuing due to uniform circular ring. Due to uniform circular ring at a point mass on its axis. This is the uniform circular ring and this is the point mass on the axis of the uniform circular ring. Now let us consider a uniform circular ring of radius a with mass m, and we are going to calculate gravitational field and gravitational potential at distance r from the center of the uniform circular ring along its axis at point P. Now a unit mass is placed at point P on the axis of the uniform circular ring. Now we know that since m is the mass of the uniform circular ring, so mass per unit length is equal to m divided by dm is equal to m divided by 2 pi a, okay, into dl. So this is the mass per unit length and this is the mass for dl length, okay. So now this is the, let us consider OP, this is, take this point as Q, okay. So here OQ is equal to A and OP is equal to R. So for this right angle triangle OPQ, hypotenuse Z is equal to under root R square plus A square, okay. So let us consider a small mass of a small length dl. This is the point mass and this is the point mass. So we are having two small masses. Leave the ring, only consider this small mass and this unit mass and find the gravitational field between these 2 points using gm by r square, okay. So g, what is, so dE, this can be calculated as dE is equal to g m, here m is dm and dm is small mass g into m, mass of this small particle, and this is the m by 2 pi a into dl, okay, gm by r square. This is the square of z. Z is r square plus a square under root, so this will be r square plus a square and under root and whole square. So this is the dE and this is a vector, so the direction is towards P to Q, towards PQ, okay. So this is a vector, so we already found this is the magnitude and this is dE. So let us consider the angle is theta, so this vector dE can be splitted into components like dE cos theta towards PO and dE sin theta perpendicular to OP towards J, okay. Similarly, let us consider another point here Q dash and find dE. For this point this is the connecting line, and for this is the DE, and this is the angle theta, same angle. This is the symmetry, both side of symmetry. So this is here DE cos theta and here DE sin theta. So from here we can understand the DE sin theta is cancelled, equal and opposite in magnitude. Okay, equal in magnitude and opposite in direction. Only DE cos theta is the addition. So now we are going to find E. So to find E, we have to integrate DE cos theta, because DE sin theta is cancelled due to equal in magnitude and opposite in direction. So we are going to integrate DE cos theta. Okay, so DE cos theta we are integrating towards P to O, towards the center. So after integrating we will get E is equal to GMR, where G is the gravitational constant, M is the mass of the ring, R is the distance of point mass from the center of the uniform circular ring, and A is the radius of the ring, R is the distance OP. So gravitational field due to uniform circular ring at a point on its axis is equal to GMR divided by A square plus R square power 3 by 2, and the direction is towards the center of the ring. Now we know the relationship between gravitational field and gravitational potential, so we can integrate this gravitational field to find the gravitational potential. So after integrating this, we will find V for the gravitational potential for the ring, uniform circular ring, and the gravitational potential is equal to minus Gm divided by A square plus R square power 1 by 2. This is the gravitational potential for the uniform circular ring, and this is a scalar quantity. Okay, and this is the gravitational field is a vector quantity, and the magnitude is GMR divided by A square plus R square power 3 by 2 towards the center of the ring. So next, third case C, due to uniform disk at a point on its axis. Now we are considering a different case. Now this is the similar case as just like ring. Now we are replacing ring from the uniform disk. Okay, so we can find the gravitational field and gravitational potential due to uniform disk at a point on its axis. We know that the disk is made up of rings. So here, so this is a disk. Let us consider a disk of radius A, and also consider a point on its axis, point P, at distance R from its center. Now consider this right angle triangle PO and Q. So for POQ, this is the OQ is A and PO is R. So from right angle triangle hypotenuse, this Z is equal to under root R square plus A square. Okay. Now let us consider a ring let us consider a ring at distance x from the center of thickness dx. So now this is the x, this is the r. So we can find this z dash. Z dash is equal to under root x square plus r square. So here, okay. Now we know that disk is made up of ring. So this is the complete disk. Now this is the small ring we have taken as ring of thickness dx. Now the mass of the disk is m. So unit mass is m by divided by area. So m by pi a square, area of the disk. So this is the mass of unit mass, pi by m by pi a square. Okay. Now a small mass, let us consider the mass of the ring is dm. Okay, so m by pi a square into 2 pi x into dx. 2 pi x is the perimeter into thickness dx. Okay, so this is the mass. This dm is the mass of this ring. Dm is the mass of this ring. Now we know that a ring, we know that the gravitational field at a point on its axis at distance r is gmr divided by a square r square power 3 by 2. So just replaces m from dm, this value with gmr divided by a square r square. Here a square is replaced by x because x is the radius of this ring and r is this, so 3 by 2. Now integrate this from this ring is, there are many rings here, this is the rings here there are many rings, so integrate this from 0 to a. So we are integrating this, and this is the final result. For gravitational field due to uniform disk at a point on its axis is E is equal to 2gm by a square bracket 1 minus cos theta, where cos theta is equal to r by z. This is the r and this is the z. Okay, and the direction is towards the center of the disk. Okay, we can also find gravitational potential by integrating gravitational field by using this formula. Okay, now let's proceed to the next. The next case is calculation of gravitational field and gravitational potential due to uniform thin spherical shell. So a spherical shell is made up of rings. So just like a ball, you take a ball and make it as a slice, so you will get a rings, lots of rings. So now here let us consider a hollow spherical shell of radius a and with mass m. Now again consider x distance from the center, a ring at an angle theta. So this is the theta angle, so this will be d theta, a small change. So this is the ring, we are considering, so we have to find this mass by total mass divided by m divided by 4 pi a square into 2 pi a sin theta. This is the a sin theta is the radius of this ring into thickness a d theta. So this is the small mass of the ring. So we can find gravitational field at point P due to this ring. We already studied the formula for the ring. Now there are two cases are possible, that when point outside the sphere and when point inside the sphere. The meaning is this point is maybe outside the sphere. This is the sphere and this point is outside the sphere. So this is the case 1, where this is the r and a. So here case 1 is r is greater than a and case 2 is r is less than a. In case of r is greater than a, P is outside the sphere, and in case of R is less than A, so P is inside the sphere. So when point mass is outside the sphere, hollow sphere, means R is greater than A, in that case gravitational field at a point is defined as vector E is equal to minus gm by r square into unit vector, and gravitational potential is equal to minus gm by r. It behaves like a point mass. The meaning is just replace the hollow sphere by a point mass and calculate the gravitational field and gravitational potential at a point from distance r. It is similar, there is no difference. The next is when point inside the sphere. When point inside the sphere, here the point is, let us consider this is the point P. Okay, so point may be inside the, in that case gravitational field is equal to 0. Gravitational field inside a uniform cell is 0, and gravitational potential is equal to minus gm by a, where a is the radius of the sphere. That is, gravitational field inside a uniform cell is 0, and gravitational potential inside a cell is constant throughout the cell. So V is equal to minus gm by a. Now graph of gravitational field versus distance of point of cell. So this is V versus R, this is E versus R. So gravitational potential versus distance. When for the hollow cell, when R is inside, then V is equal to constant. So V is the constant. For outside, it is V is inversely proportional to R. Okay, and for gravitational field, E inside is equal to 0, and for outside point, E is inversely proportional to R square. Okay, so for the cell, gravitational potential versus distance is a continuous graph, and gravitational field versus distance is a discontinuous graph. Now points to ponder. Concept 1. The force of attraction between a hollow spherical cell of uniform density and a point mass situated outside is just as if the entire mass of the cell is concentrated at the center of the cell. Means this is the cell, point mass is outside, other mass. Now we have to calculate the force. Just replace this as a mass, point mass, and this is the P. Now calculate for this and this will give the same result. Concept 2. The force of attraction due to a hollow spherical cell of uniform density on a point mass situated inside is 0. The force of, since E inside is equal to 0, so F is equal to, we know that F is equal to ME, right? If E is equal to 0, is hence F is equal to 0. Okay. Now calculation of gravitational field and gravitational potential. The next case is due to a uniform solid sphere. So solid sphere is made up of hollow cells, just like onion. Onion is a solid sphere in likewise in shape, and it is made up of hollow cells. Okay, so we already studied for the hollow shell. We already studied E and V for hollow shell. So we can find for a small mass of thickness dx, and we can integrate this. Okay, so case 1 is when point outside the sphere, point is outside the sphere. In that case, E is equal to minus gm by r square and V is equal to minus gm by r, just like point mass. Okay, and direction is towards the center. And case 2 is when point is inside, when r is less than a. In that case, E is equal to, gravitational field is equal to minus gmr by aq, where r is the distance and a is the radius of the sphere. This is the magnitude, and the direction is unit vector. The meaning is E is equal to gm by aq into r. This is the magnitude, and direction is towards the center of the sphere. And the next is V can be represented at, for inside point, V can be represented at V out and V inner, like this. Let us consider this is the point when r is smaller than a. In that case, this is considered, this is the one case and this is the other case. So this is the V in, this is the V out. So we have to add this, then we will get V total. So here, okay, so V outer is equal to minus 3 gm 2aq a square minus r square, and V inner is equal to minus gm rq aq. Okay, so we are adding this, V is equal to minus gm 2aq into 3a square minus r square, where a is the radius of the sphere. Okay, at the center of the sphere, the potential, we have to put r is equal to 0, we will get V is equal to minus 3 gm by 2a. Graph of the gravitational field versus distance of point for a sphere. For a sphere, E versus r. For the inside point, E is directly proportional to r. Okay, for outside point, E is directly proportional to 1 by r square. So it is a continuous graph. Now question 1, let V and E are the gravitational potential and gravitational field at a distance r from the center of a uniform spherical shell. Consider the following two statements. The plot of V against r is discontinuous. The plot of E against r is discontinuous. Both A and B are correct. Both A correct. Second option is A correct but B wrong. Third option is B correct, A wrong, and D is both A and B are wrong. We already studied V is continuous for shell, like this, and this is the E versus R, this is the V versus R. So plot of V against R is discontinuous, this is wrong. Plot of E against R is discontinuous, this is correct. So option B is correct, A is wrong. B is correct, A is wrong. So option C is the correct answer. Okay, now next question is, a uniform spherical shell gradually sinks, maintaining its shape. The gravitational potential at the center. Gravitational potential at center is equal to minus gm by a, where a is the radius. When uniform spherical shell gradually shrinks, it will decrease in radius. Radius will decrease. When radius A decreases, this overall value will increase. But due to negative sign, this overall will decrease. Okay, so option B is the correct answer. Okay, so gravitational potential at the center will decrease. Thank you. This part is completed. We will continue in the next part.
Here at Ask IITians, you can ask your queries and doubts. Only you have to do is you have to go to www.askiitians.com. On the website, you will find a tab as Ask a Question. Click on tab Ask a Question. A new page will be open, and on the discussion board, right side of the screen, you will find Ask Expert. Under this section, you have to select your categories from which your questions belongs. For example, thermal physics. Now you have to type your question here, or you can attach the snapshot of your question here, and after that you have to click on get answer. We will get you revert within 24 to 48 hours.
So students, we have discussed about the calculation of gravitational field and gravitational potential at various points due to various shapes. We have also discussed about the graphs between gravitational field and distance and gravitational potential and distance for the hollow shells and for the sphere. In the next part, we are going to discuss about the variation of accretion due to gravity. So stay tuned. Thank you.